Sequencers are probably the most important part of modular. If you're into that whole thing some people do sometimes, music. Random numbers pumped into a quantizer can get you pretty far, but to get a repeatable melody, you need something that can output notes in a sequence, and for that you're going to need a sequencer. NerdSEQ is one of the most popular Euro-rack sequencers, and uses a tracker-type setup where you program each note down the line in this handy little interface that feels real 90s, and looks like no matter what you put in, vaporwave will come out of it. The biggest issue I have with NerdSEQ is that it costs $700, and it just has too many features. Like, look at all those. Oh, apparently you can hook up a Sega gamepad to this thing, and that is actually pretty cool. I wish I could do that. So instead of spending $700, I'm going to spend dozens of hours building my own version, and making it substantially worse, but also it'll only be like $50. So by that logic, if it's still 10 times worse, I still save $20, which is good enough for me. Plus it'll still be better than Behringer. NerdSEQ has 6 channels with 255 rows each. We're going to pare that down in our version to only 2 channels with a maximum of 16 rows. And then, instead of the cool full-color display, we'll crunch everything together into a 4-character, 16-segment display. After some trial and error on the display format, I decided on this setup where we have the first character displaying the step number, and then the second one is this useless arrow symbol to make the design look more sleek and modern. Then the last 2 characters are the currently selected MIDI note name for that step number. I realized that I can control those little dots at the bottom, so the dot in the note name means sharp, like B sharp, D sharp, but it's B dot, D dot, you get it. You get it. We can choose the number of steps with one potentiometer, and then use the other one to choose the note number. Then a button to advance to the next step, and a switch to switch between the 2 channels. Oh yeah, the other little dot next to the step number tells us if we're currently selecting channel 1 or 2. This is an information-dense little screen here. And these are the basics. We select a note and advance through step by step until we programmed an entire sequence. So if you watched the previous episode, you might remember the trouble I had with potentiometer noise. I had an excellent suggestion to put a capacitor in parallel from the data pin to ground on that potentiometer to reduce noise, which, depending on how much electronics education you have, either seems like the most basic thing in the world to you, or crazy magic stuff that seems like it would break something. And even if you know how to do this sort of thing, there is the additional layer that often gets missed. Why does that work? What's this capacitor even doing? A capacitor in parallel to ground works as a low-pass filter. The capacitor here is pretty much working like a sponge. Small fluctuations in voltage get sucked up no problem, but big changes cause our capacitor sponge to get saturated and give up. This makes a low-pass filter because only the slow-moving bits get through. There is this weirdly nice equation for what our frequency cutoff is. 1 over 2 times pi times the resistance times the capacitance, where resistance is in ohms, capacitance is in farads. And you know I just can't leave this here. When 2 pi shows up, there has to be circles around somewhere, and what do frequency and capacitors have to do with circles? But we'll have to put a pin in that and come back later, or else I'll go completely off the rails. So that'll be another video. In our noise-canceling example, I used a 1 microfarad capacitor in parallel to a 50,000 ohm variable resistor. A microfarad is 1/millionth of a farad, the same way a microfarad is 1/millionth of a farad. Calculating all this out, we get about 3.2 Hz for a cutoff value. It would help a lot here if I had a noise profile to compare against to see if the 3.2 is the right number for the job here, but instead I'm going to go with the tried and true, that feels like a number I could get behind, strategy, and move on. Plus it feels less noisy, and I think that's all that matters. Back to the real world, let's move our breadboard machinations over to something a little bit more permanent. To recap here, we have a clock input jack, a note select knob with noise reducing capacitor, 2 channels of output jacks, left and right, our display, and a jack and a knob combo for the number of step selection. Off to the side, we also have a manual step advance button and a channel select switch, which we'll solder onto the back of the board later because they don't fit onto the perf board. And after some cute soldering, we have our board, and we need to build an enclosure around it now. I'm once again trying the poke holes in a piece of paper strategy to make a cutting guide for our box. Honestly, it doesn't really work that well because the paper sort of warps while poking the holes in, but it is ballpark enough that I can work with it. I still only own a drill, so the area where the display will go is created by just drilling a bunch of small holes close together. I have some tape to cover this up, so I'm not that worried about it. And back to our button and switch from earlier, they both need ground connections. Then we can use the digital input pin set to pull up mode to detect if they're connected to ground or unconnected. This way we don't even have to worry about a 3.3 volts connection, and it's so much nicer. Oh, also put a digital out pin to ground for the LED that's onboard our button. I can't even remember if I wrote any code to control that LED, but at least it's wired in. And there we go. Everything fits, and now I can turn my brain off and paint the box for a little bit. Because the tape I'm going to use to hide my mistakes is black electrical tape, we're going with black nail polish today, so it will all blend together. So let's just sit back for a second, listen to some synth music that you should totally buy on Bandcamp, link is in the description. So now that we've just about finished this thing up, there is one more thing that I've glossed over that we should probably talk about. This module outputs a different MIDI note value based on what note is selected on each step, but how does it do that? The modular synth only talks in volts and not notes, so we need to come up with a scheme to describe what voltage means so other modules can use that information. Eurorack uses the standard of 1 volt per octave. Usually we have 12 semitones per octave, so each note increments by 0.0875 of a volt. The system that I'm building runs on 5-volt USB and uses a 0 to 3.3 volt range on signal pass between modules, instead of Eurorack's negative 10 volts to 10 volt system. So if we use Eurorack's 1 volt per octave system here directly, I would only have a little over 3 octaves to work with, which just doesn't feel like enough. Looks like we have to go our own way. Standard MIDI has 128 notes in it, which seems like a bit much, because some of those are outside of the range of human hearing. So I settled on an 88 note range of what pianos have, which starts at A0 and goes up to C8. I only partially did this because starting on A0 makes the code a lot simpler. The internal code for these modules reads voltage values as a 16-bit value from 0 to 65,000, which makes each note a little less than 750 units, which seems doable to me. Noise tends to be on the order of 100 to 500 at the worst, so we should be able to get our notes interpreted correctly. From here, it's actually really easy to figure out frequency based on the value that we get. Just divide by 745 to get the note number, then take the note number and plug it into this equation, where B is our base frequency, A0, in this case, which is 27.5 Hz. The 2 to the n over 12 part divides our scale into 12 equal divisions, that 12-tone equal temperament scale everyone loves so much. If you want to do microtonal stuff instead, you just have to change this 12 to another value. I've heard 37 is cool. I'm sticking to just 12 tet for my mod synth, so I round n to be an integer, and then we get out the frequency value encoded by our sequencer. Zooming back out, let's put everything together. And there we go, a fully functional modular sequencer. Let's see how it sounds. Thanks for following along with this one. I hope you learned something new. If you are actually interested in building one of these for real, I have code and schematics and stuff in GitHub linked in the description, but be warned, this module as designed will not work with Eurorack stuff directly. 10 volts is not nice for all of these small circuits. You could probably pretty easily put in some voltage shifters to make this one work, but I'll leave that as an exercise to the reader. Anyway, I'll see y'all for the next one. Bye!